Yeah, so I hope my screen is visible to you.
Yes, sir.
Okay, great, thanks. So let's move forward. I hope you are able to read the problem. It is based on losses and efficiency. So a 15 kilowatt 220 volt shunt motor has 110 ohm field resistance. Its maximum efficiency is given. So I hope you are aware with the maximum efficiency condition. When does it occur? What is the condition for maximum efficiency? When constant losses is equal to variable losses. Okay. So that value is given 83%. Now it reaches its maximum efficiency when it delivers 71% of its full load. Okay. So maximum efficiency is at 71% of full load, it means 0.71 I rated. Okay. And a speed at that particular load is 1100 rpm. Now, when the motor is found to draw 91 amp current from the supply, then we need to find the speed. So it's pretty obvious. We have solved so many questions based on ratio of speeds and all. So when you are required to calculate the value of a speed with different conditions, indirectly we are referring to find out the back EMF at those conditions, right? So first we need to find out the back EMF at initial condition. Now when the motor is drawing 91 ampere of current from the supply, at that condition, how much back EMF will be there in the circuit? I hope you are able to get the question, right? So case one we will make. When I is equal to 0.71 I rated. Now, maximum efficiency condition is that, okay, so at maximum efficiency, constant losses are equal to variable losses, right? So, uh, first we have to find out the, you know, what are the currents at that loading. So, how to find out the armature current, because we don't know neither armature current nor line current. So, but I think we can find out the field current at that load. Another way is that first we can find out the rated current, and we just take the 71 percentage of the rated current, and that will be our line current at that condition, right? So let us move ahead. The output is 15 kilowatt and efficiency is 83%. So input power we can write 15 by 0.83. How much it will give? It is approximately 18 kilowatt. Now, this we can write it equal to Vt into IL, okay? Because input in the motor will go, so this is a shunt motor, whatever VTIL in the shunt motor, let me draw a circuit for that. This is IA, this is IF. Right? So input power is nothing but VT into IL. From this circuit you can see. So VT is given in the problem, that is 220 volt. So IL we can calculate 18,000 divided by 220. That will be 81.81 amps. Okay. Now this is the rated line current, but the condition of maximum efficiency occurs at 71% of IL rated. That will be okay. So how much it will give? 58 amps. Now, with this 58 amps of current, and we have, you know, field resistance is provided as 110 ohms, right? So this RF is 110 ohms. So field current we can calculate. That will be fixed for shunt motor. That is nothing but 220 divided by 110 is 2 amps. Now, at maximum efficiency, IL will be 58, sorry, IA, not IL. Armature current we want to find out. 58 minus 2, that will be 56 amps. Okay, so we have calculated field current and armature current at that condition. So I think now we are good to calculate back EMF. So back EMF will be VT minus IRA. VT is 220 minus 56 into RA. RA are we given in the problem? So RA is not given in the problem. Now we have a stuck here. What is the solution? We don't know RA, and hence we cannot calculate EB, and hence we will not be able to calculate data speed. So what is the solution? Yeah, anyone? Neeraj, Deepak? I hope I am audible, right?
Yes, sir, you are audible.
Okay,
We are
okay,
not getting
okay,
any ideas how to handle this situation.
okay, okay, no problem. So, see, one thing we can, what are the conditions at which we calculated this IA and all? The
At
condition
rated
was
load.
maximum rated, not rated load, at 71% of rated load, but maximum
Okay.
efficiency condition. Yeah, so at maximum efficiency condition, that is 71% of full load current. So, and we concluded one more thing, that at maximum efficiency, constant losses are equal to variable losses. So, will it be sufficient to provide any other data?
Sir, efficiency is 83%, then losses will be 27%. This 27% losses can be
Exactly.
divided
Yes.
equally.
Yes. So now you got that. So yeah, we are given with the losses indirectly, and we have to divide it by two to get the variable losses. And variable losses is nothing but armature loss in this case. So from that expression, so let me find out the 29% of the loss. So 29% loss is equal to how much? 15,000, 15 kilowatt into 29. So that will be losses, right? So 15,000 into 0.29, 4350, 4350 watts. Uh, 15 kilowatt was the output power, right? Input power also we calculated. So 18 kilowatt is the input power. Okay. See, we have committed, I have committed a mistake. This 15 kilowatt is not output power, but and this 83%, so 17% is the efficiency. Since 83% is the efficiency of the machine, so 17% will be the losses, right?
Yes, sir.
Yeah. So this will be 17%. So losses will be 17%, and this will be 0.7 into 18 kilowatt. It will be equal to 18 into 0.17. It will be 3 kilowatt. Okay. So 3 kilowatt are the losses. So constant loss and variable loss. So IS, I can divide it by 2. So variable loss.
Sir, 18 kilowatt is input power.
18 is the input power.
Okay.
So 3 kilowatt divided by 2, it will be 1.5 kilowatt. And I can equate it to equal to IARA. Okay. And IA we have calculated 56 amps. So RA we can calculate from this expression. 1500 divided by IA is 56 square. Okay, so it will be 1500 divided by 56 square. It will be equal to 0.47 ohm or 0.48, 478, so 0.48. So any doubt in this? We have calculated RA, we have calculated, now we can calculate EB, right? Just plugging in the value of RA here. So
Okay.
I will plug in 220 minus 56 into 0.48. So it will be 220 minus 56 into 0.48, 193.12. So this is EB1. At this back EMF, we have the speed is equal to 1100 RPM, right? That is provided in the problem at 1100 RPM. Now we have to find out the speed when the motor is drawing 91 amps. Okay, so when it is drawing 91 amps, now we can find out the back EMF simply by KVL because we know RA and we know field drop. Okay, so for second case, when line current is 91, EB will be equal to VT, that is 220 minus IA. So how much IA? Since IL is 91 amps and field current is 2 amps, so it will be 89 amps, right?
Yes, sir.
Into 0.48. So it will give us 220 minus 89 into 0.48, 177.28. So now we have to find out the speed at this back EMF. So we will take the ratio, right? N2 by N1 is equal to EB2 by EB1. So N2 will be equal to EB2 is 177.28, EB1 is 193.12 into 1100 RPM. So it will give us in RPM only 177.28 into 1100 divided by 193.12. So it will be equal to 1010 RPM approximately. So this is the speed we will be having at this condition. Okay. So any final doubt in this part?
Sir, in case of DC shunt motor, we only consider variable loss of armature resistance, and but in
Yes.
case of series motor, we have to consider field resistance as well.
Yes. So why is that? You tell me.
Sir, I think in case of DC shunt motor, field current will get fixed.
Yes, because it
Yeah,
is connected
because it,
directly to voltage, right? But
yes, sir.
in DC series motor, whenever you are changing the load, what is getting changed as well?
Current.
Field current. Field current is changing as well. When you are changing the load current or armature current or line current, you are changing the field current as well.
Yes, sir.
Yeah. So that is the reason that you will get, you know, you will get field losses as well be included in the variable losses. Okay. Any other question?
Sir, whenever
So,
there is a statement like this that motor is found to draw 91 amperes current,
mhm.
how are we supposed to know that it is talking about the current from the supply or current to the armature only?
So whenever motor is drawing, so motor will draw from line only, right?
Yes, sir.
Yeah, it cannot draw from armature. So you know anything is stated like it is drawing from supply. So it is by default line current. Otherwise, if they will mention that this is armature current, then you can explicitly see that it is mentioned in the problem. Otherwise, if it is drawing some current from the supply, it will be written like it is drawing from that supply, right? So it is
Okay, sir.
pretty clear from this statement that motor is found to draw 91 amp current from the supply.
Okay, sir.
Yeah. So any other doubt in this part?
No,
Sir,
sir.
in case of motor, they always given output power in
Yeah.
question.
Yes. Yes. Now, in case of any machine, whatever ratings are provided here, that will be output power only. Even in generator also, whatever you get whenever not even generator for any machine, the ratings are given in terms of output power. Otherwise, if they want to provide you input data, they will mention the kVA rating. Then by
Yes,
multiplying the power factor in that expression, you can get input or output power. So
yes, sir.
this data is always your output rated power. Okay.
Okay, sir.
Okay. So in this problem, now we have to find the efficiency at 91 current. Okay. So at 91 amps, what will be the efficiency? So for calculating the efficiency, one thing is output power divided by P input, right? P input we can calculate, right? How much it will
Yes,
be? 220
220 into
into,
91.
yes. So it will be equal to 220 watts. Now, to calculate output power, we have to, do P input minus losses. Now, this is the only tricky part. What will be the losses at this current? Because earlier we just found the losses and we divided it by 2. But now we will have, you know, different sets of losses. So first
Yes.
thing, we will go step by step. We will segregate all the losses. One will be the armature loss, armature copper loss. So armature current IA square RA, and IA is nothing but 91 minus 2. So 89 amps a square into RA. RA we found in part A, that is 0.48. So it will be equal to 89 square into 0.48, 3802 watts. Okay. So we found armature copper loss. Now, what about field loss? So it is 2 amps into RF. RF is 110 ohm. It is 440. Now, the last part is the, you know, no load losses, right? So no load rotational and magnetic losses.
So it will remain the same 1530.
Yeah, exactly. So it will be equal to 50% of whatever we calculated in first case. So 3 kilowatt was the total losses. So we divided and 50% we accounted for variable losses. Other 50% will be for constant losses. And that constant losses will be accounted for no load rotational and magnetic losses. So it will be fixed. I hope everyone got it. So it will be equal to 1.5 kilowatt. Okay. So now we have accounted all the losses. Now we can go with the efficiency. Okay. So it is to P output by P input. So P output is 220 minus 1500 minus 440 minus 3802 divided by 220. It will be equal to 71.3%.
Yes, sir.
Yeah.
Sir,
Yeah.
but in this case, we have included the field losses in the constant losses.
Field losses we have included in the constant losses. Uh,
No, sir, it is calculated separately for 40 watts.
Yes, yes. We haven't included that field losses in constant losses.
But sir, while calculating the RA, we did not consider it as a variable losses.
Uh, Sorry, can you repeat?
Sir, when we were calculating the RA,
Hmm.
IA square RA, and then we did not consider it as a variable losses. Why?
IA square RA, we did not consider it as variable losses. Okay. Hmm. See, okay, yeah, I guess you are right because we have included field losses in constant losses, right? I guess we have included field losses in constant losses because in this case also in part A also, yeah, you are right, Deepak. So we have included field losses in constant losses. So we have to remove this component. We have already included here. Okay, that 440 watt is included in this 1.5 kilowatt. Okay,
Yes, sir.
yeah.
Sir, then I think
Efficiency will
our
get
RA
changed.
calculation,
Sorry, go ahead.
then we also have to revise the calculation for RA.
No, why?
Sir, the 17% of that 18 kilowatt
Mm-hmm.
will include the field losses too.
Yeah,
But we have
17% will account for total losses at that
total
point.
loss.
Hmm.
So then we have first we have to subtract 440 watts from this 3 kilowatt. Then we have to divide it by 2.
Mm, no. See. Okay. Yeah. You have a point. Hmm. Yes. Okay, let me. This variable loss. So total loss is 3 kilowatt. Now armature copper loss is 1.5 kilowatt. Okay, rest field copper loss plus no load rotational loss plus magnetic loss is equal to 1.5 kilowatt here, right? Do you agree on this point?
Yes, sir.
Okay. You, Neeraj?
हाँ सर ऐसा है तब ठीक है.
Okay. Now we will straight away what we do. Okay, so we have this losses. Now the rest loss is 1.5 kilowatt, and based on that, we are calculating IA square RA,
Okay
right?
sir.
So that will give RA, and that RA value is correct. Now, with this loss and plus IA square RA at 91 amps, we will add, and that will give us the total loss, right?
Yes.
Yeah. So now what I will do, I will just, you know, replace this. This is 1.5 kilowatt, and this is 81, sorry, 89 square into 0.48. I hope it is fine now, right?
Yes.
3802.081. Now how much it will be? Minus 1500 minus. Okay, this term will be 1 since field losses was already included. Yeah, thanks for pointing out. This is very important thing. I guess I committed mistake here, but thanks for pointing it out. Is equal to 73.51% efficiency. Okay.
Okay, sir.
Any final doubt in this part or in this entire question?
Sir, we can include the field losses in constant losses only in case of shunt machines, no, sir?
Only
In
in
series
case of
OC.
shunt machine and separately excited also wherever it is not mentioned. And if field is fixed, but in series machine and I think compound machine kind of there you have to read a problem carefully in which case your field is varying. In
Okay, sir.
certain cases they may connect rheostat and all and they can vary the field. So in that case you need to just give a attention to the problem.
Okay, sir.
Okay then, so let's move ahead with the next problem. Okay, so I hope you are able to read the problem. I will read it for you as well. At no load, 2.5 kilowatt 100-volt DC shunt motor takes 1.5 ampere current and runs at 1080 RPM. Okay, armature resistance is 0.35 ohm. Field resistance is 400 ohm. Estimate the efficiency at rated load. Okay, so for efficiency again, we just need the losses. We know the power, right? So from this statement, we can conclude that output power is 2.5 kilowatt. Mm, 1.5 ampere this machine is taking. It means IL is 1.5 ampere at no load. Okay. And IF field current will be 100 volt divided by 400 ohms. It will be 0.25 amps. So in last lecture also, I told you that no load rotational and magnetic losses will be equal to how much EB into no load armature current, right? So at no load, EB will be equal to VT 100 minus IA will be how much? 1.5 minus 0.2.5. So 1.25 into RA is 0.35. It will be equal to
99.56.
99.56 volt. So no load, mechanical and magnetic losses will be equal to how much? 99.56 into
1.25.
1.25. So it will give us the value. So it is
124.45.
124.45 watts. Okay. So we are done with no load rotational and magnetic losses. Now, what about armature losses and field losses, right? So, oh, no, no. Again, we are committing that mistake. I guess here, this is the no load losses. First, we calculate the, no, in this loss, field loss is not included, right? In this loss, no load mechanical means rotational loss and magnetic loss. So in this loss, because it is not a fixed loss, means it is a part of constant losses, but it is not the total loss, total constant loss. So we have to calculate field copper loss. Field copper loss will be equal to IF we have calculated 0.25 ampere and our RF is 400. So 400 into 0.25 ampere. So it will be 400 divided by 16. So it will come out to be approximately
25.
20, 25 watt. So now it is total constant losses of the machine. The variable loss is armature loss, right? So armature copper loss at no load is 1.25 square into RA. RA is 0.3, 0.35. It is 0.54 watt. This will be armature copper loss. Now we had to find out the efficiency. But one catch is there. We have to find out the efficiency at rated load. Okay, not at no load. But we don't know the rated current. But can we find that?
Yes, sir.
Yeah. So what should be the way to find out that current?
So rated power divided by voltage.
Rated power divided by voltage. Yes. So
This will give the current. We will subtract field current from it.
okay. Okay. So let us assume that, okay, we have to assume one thing and we can subtract from that. So IL rated will be equal to how much? Let's suppose I we are assuming at that condition, and it is nothing but 2500 divided by VT. VT is
100 watt.
100 volt. Yeah. Okay. Is it fine?
Okay, sir.
But I don't think it is fine because 2500 is the output power, not input power,
Yes,
and
sir.
this line current is corresponding to the input power. So we have to add the losses here. Okay.
Sir, I think we can do
Hmm.
that. We They have provide output power.
Hmm.
So and we know no load constant losses like
Hmm.
field losses and rotational losses.
Hmm.
So we can subtract from the output power and we get EB into IA.
Yeah, yeah. So that is also correct. Yeah. So anyway, uh, we have calculated all the no load losses, right? But this no load rotational and magnetic losses will be same. field copper losses will be same. Only thing change will armature copper loss, isn't it?
Yes, sir.
Yes, sir.
Yeah. So my total losses will be we will add 124.45 plus 25 first, plus armature losses. So it will be IA square. RA is 0.35. Okay. So 0.35 IA square because we don't know IA, right? Now this is P input. So again I can write IL is equal to P input by 100. So P input we can write output 2500 plus losses 124.45 plus 25 plus 0.35 IA square divided by 100. So now if we convert IL to IA, that then it will become a quadratic equation, right? So that quadratic equation will be 0.35 IA square plus 2500 plus 124.45 plus 25 2649.45 is equal to 100 IL. And further, if I want to simplify 0.35 IA square minus 100 IL, we can write IF is how much? IF is 0.25 amps. So 25 plus IA plus 2649.45 is equal to 0. Okay, I hope you are getting it.
Yes, sir.
Yeah. So minus 25 plus 2649.45 minus 100 IA. If you solve this quadratic equation, you will get the answer. So let me solve it. 2649.45 plus minus 25. So this term will become if I put them in the equation, I will get IA is equal to 256.478 and another value is 29.236 amps. Okay, so which value I should consider?
Sir,
So
29.
Yeah, 29 is the very real value. 256 is way higher. Okay, so 29.36 ampere is the expected armature current. And after getting this armature current, now I think we will be able to find out the efficiency because we have already calculated all the losses. Just we needed armature copper losses at this point, right? So yeah, so here we can replace this, no, here, this. So armature copper losses is 29 point, how much? 36 square into RA is 0.35. 301.7 watts. Okay, so this is 301.7 watts. So what will be this total losses? 124.45 plus 25 plus 301.7. Okay, so it will be 451.15 watt. Okay, so we are done with the total losses. Now we can find out the efficiency. Output power is nothing but 2500 divided by 451.15 plus output power. This is rated output power 2500, right? So this will give us the losses 2500 divided by 2500 plus 451.15. So it will give us 0.84. So it means this machine is 84% efficient. Okay, any doubt in this?
No, sir.
Okay. So we should move ahead with another problem. Okay, so this is again similar kind of problem, but here just the total brush drop is provided, and we have to find out the full load efficiency. And this is a DC shunt motor, and no load current is given, right? So, okay, let us move ahead with the no load losses. It will be how much? First, we should find out the field current. So field current is
1 ampere.
1 amps. Yes. So no load armature current will be equal to 1.5 amps, and no load losses will be equal to, first we need to find out the EB for that, EB at no load. That will be equal to 200 minus this brush drop is 1 volt, okay, minus IARA, that is 1.5 into RA is 0.75, minus 1 minus 1.5 into 0.75, it will be 197.875 volt. Okay, now the no load losses will be 197.875 into IA0 1.5, that will be 296.8. Okay, so this is the no load losses. Now, the next part is we have to find out the efficiency at full load. So again, to find out the full load, again, we have to make the same process to make a quadratic equation, right? So P losses is equal to no load losses, that is 296.81, plus field loss will be 1 square into field resistance is 200, plus other is rated current armature loss. So IA square RA. RA is also given, that is 0.75, and one more component will be brush drop losses, right? So brush will be connected to the armature, so whatever the current will be there, that will be included. So brush drop is 1 volt into IA, so 1 into I. Okay, so this is the total losses. I hope it is fine till here. And after that, uh, we have to put here, we are given with output power, we need the efficiency. So we can equate to the input current or input power is equal to output plus losses. Then that will make a simplification of the quadratic equation. So input power will be output power plus losses. So input power will be 200 into IL is equal to output power is 2500. No, here 8 kilowatt, right? 8 kilowatt. So 8 kilowatt plus 296.81 plus 200 plus 0.75 IA square plus IA. And IL we can write IF plus IA, and IF we have already calculated 1 amp, so 200 1 plus IA is equal to, I will calculate this all constant terms. 8,000 plus 296.81 plus 200 plus 0.75 IA square plus IA. So if I make a quadratic equation, it will be plus IA minus 200 IA, so minus 199 IA, plus 8496.81 minus 200, it will be 8296.81 is equal to 0. Now it's just that we have to calculate the value of IA. Again, solve the quadratic equation. It will be 213.52 amps, and that is 51.8. So again, we have to go ahead with 51.8 ampere because that is a reasonable amount of armature current. So now what will be the full load efficiency? First, we have to find out the full load losses. So just put in here 51.8 amps and here also 51.8 amps. So let me calculate that. 296.81 plus 200 plus 51.8 square into 0.75 plus 51.8. So it is equal to 2561. Okay, that. Right. So now efficiency will be output, and that is 8 kilowatt divided by output plus losses 2561. So it will be 8000 divided by 8000 plus 2561 is equal to 75.75%. Okay, any doubt? It was pretty repetition of the last problem, but just the addition of brush losses. But I hope it will, provide you just practice of such type of problems.
Sir,
Yeah, go ahead.
by mistake, let us we have taken the value of IA is 213.52. Then the efficiency will go down very.
How much? 230 point. Okay, so that will not be anyhow reasonable if you calculate. 230 point. Okay, let me calculate armature losses at that condition. So 213.52 square into RA. RA is 0.75. So this particular loss is itself higher than the rating of the machine. Okay. So this is coming out to be 34 kilowatt, whereas the rating of the machine is 8 kilowatt.
Yes, sir.
So there itself only you will get to know that you have committed some mistake also. Okay.
Yes, sir.
Yeah. So any final doubt till this point? Okay, so I will take a problem based on Hopkinson test. Okay, so let me take that problem. You have studied Hopkinson's test, right? So it is a kind of regenerative test where two machines are coupled with each other. Do you have any idea about Hopkinson's test or not?
Sir, please explain some little bit.
Okay. So this is the circuit of Hopkinson test. Okay. Here, variable field of the motor, right? This is the variable field of the motor. This is the variable field resistance of the generator. Now, a DC supply is providing, field current to the motor and field current to the generator. I hope you are able to see. And armature current. Okay. That armature current will be going directly to the motor. This is the motor. I hope you are able to see. Along with that armature current, one more component of armature current will go to the motor. That will be from generator. So whatever armature current in motor, that is coming from the supply as well as from generator. Okay. So armature current to the motor is different from whatever coming from the supply, and the highest current is flowing in the armature of the motor. Okay, so if you are given in the problem the test data, right, in that it will not be specified this is the motor field current, this is the motor armature current, this is the generator armature current. You have to identify from the data. Okay, so whenever you see that significant amount of armature current, that will be higher value will be for corresponding to motor, and the lower value will be corresponding to the generator. Okay, till here it is fine.
And sir, field both the DC machines of field winding we have given a directly supply.
Direct supply, but we can vary with the rheostat. You can see here, right? Both can vary.
Yes, sir.
Yeah. So if they are varying, right? So we can do field control. We can either reduce or increase the field current. But what are the consequences of that? That we will have to see. Okay. So, and in Hopkinson's test, since it is a regenerative test, okay, two DC shunt machines are coupled mechanically, and one of the machines one of the machines is acting as a motor, the other is acting as a generator. Okay, so whatever the generator is supplying, that is going to the motor, and whatever motor is rotating, that shaft is connected to the generator. So ideally there should not be any losses. So this setups, once you have turned on, it should continue to run till infinite time, because ideally there will not be any losses, but practically there are certain losses. But this kind of test is done when we need to test the machine setups for long duration of the time. Okay, so, and here from this machine we can, sorry, from this test we can identify the efficiency of the machine. Okay, so one of the machines, let's say a DC motor, we have provided the supply, we rotate it, and we brought it to the rated speed. Now when the motor is at rated speed, your generator will also be at rated speed. Okay, and in this machine, excitation current in the generator is kept high always than excitation current of motor. Okay, so once, why is that so? Because there will be some field supply required for the motor, that is coming from the DC supply or whatever supply is provided. But this field current is kept higher such that it will this generator will be required. Once, let me put it this way. Okay, even though you have field current, once you have higher field current, your EMF generated will be higher. Okay, and this EMF is higher than motor EMF, right? And this EAG is higher than EAM. Okay, and this will lead to IAG, increment in IAG and IAM. So what it will do, if you keep the excitation of the generator higher than the motor, some part of it will supply to the motor. So you can see that you are increasing the field of the generator and your armature of the motor is increasing, right? And another thing is, even if you reduce the field current of motor, so what will happen? The speed can increase of the motor, right? Now this will lead to increase in the generated voltage of generator. How? You are reducing the field current of the motor, but it is increasing the field induced EMF of generator. How?
So due to reducing the flux of motor
Huh.
winding, motor field winding.
Yeah, and motor is directly coupled to the generator. Hence, generator is also having that speed, right? So hence,
Yes, sir.
induced EMF of generator will be increased, and it will again be higher than motor induced EMF, and hence IAG will also increase, and it will lead to increment in IA. So whenever in the test data you see that armature current, okay, armature current, sorry, not armature current, armature current we have already talked about. It will be higher than all the currents, and about field current, you can identify by having which field current will be higher, generator or motor. Hmm? How
Generator
will
field
you?
will be higher, sir.
Yeah, generator field current will be higher, and you know why?
Sir, why?
Okay, so actually, some component IAM is constituting by IA and IAG, right? And IAM, from this node, you can see IAM can be increased by increasing IAG, isn't it? When this switch is
Yes, sir.
closed, IAM can be increased by increasing IAG.
Okay.
So the load from the supply will be reduced. The supply capability, the rating of this supply will be reduced, isn't it?
No, sir, I am not getting what you want to say.
Sorry. Could you please repeat? I didn't get you.
Sir, I am not getting what are you saying.
Okay, so see, if you have IFG higher value, right? What did we conclude here? If you are increasing IFG, what are you gaining in terms of IAM, right? If you're increasing IFG, you are gaining in terms of IAM.
Okay.
And IAM is what? IAM is nothing but IA plus IAG.
Yes, sir. IA plus IH.
And if you are able to increase this IAG, or if you are able to increase this IAM, it means your IA can be reduced for the same power, right? And that, are you getting this point?
Okay.
See, IAM
Yes,
is
sir.
equal
Yes, sir.
to,
Yes, sir.
yeah. So if you are able to reduce, it means your load from the supply, or you can reduce, you can operate same ratings of the motor with lower rating of the supply.
Yes, sir.
Yeah. So
But
whenever in the
what's the field current of motor will be same now?
field current of the motor, yeah, whatever field current, you can vary field current because it is connected parallel to that, right? But this
Yes,
this
sir.
IA, this IA will depend, right? What is the rating of the machine? VT into IA, right? Of DC machine. VT into IL, and IL is nothing but IF plus IA. VT into IL is the rating of the machine, right? Input power. That is proportional to rating. And if you are, this is IF plus IA, and even though it is a constant IF, you are reducing IA, it means you are reducing the rating of the machine. Okay, just think once more after the session. I hope you will be able to get it.
Yes, sir. Sure.
Yeah. So two conclusions from this much theory, that you have to identify the data. Okay. Now coming back with a numerical problem. Okay, first let us you know simplify a bit further. How to calculate what components of losses and power, right? So total input to the circuit will be how much? Just now we discussed. It will be from this circuit. Let me bring it down. Okay, so from this circuit, how much will be input power? It will be Vt into Ia, right? That will be input power.
Sir,
Total
IL.
I okay, yeah, that will be from here. I am saying to the armature. Let me rephrase it. Total power input to armature. We are assuming that this field power will be constant, so we are focusing on armature. This Vt into Ia. This. Okay, how that component is distributed, that we are more interested. Okay.
Yes, sir.
Okay. So now that is the armature input power. We have certain losses. Windage plus frictional losses means no load losses, basically. No load magnetic losses, magnetic and mechanical losses will be how much? And because this IA is responsible for the losses in both the machines. Okay, so with this test we will be finding the power and losses of both the machines plus whatever the stray losses. That will be equal to Vt into Ia minus, this is the input of armature, right? Minus IAM square RAM minus IAG square RAG. Okay, so this will be the total, constant losses, excluding field current. We are not including field current. Okay, till here, I hope it is fine. Now, for each machine, this is for both the machines. Combination of motor and generator. So now, no load losses for each machine will be how much? It will uh, it will not be ideally half, but to identify the numerical values or to identify the approximate value, we just divided by half. Okay, this is for each machine. Now you can account for field losses separately. Field losses will be Vt into IFM plus Vt into IFG. Okay. Now the total losses. How to the objective of this test is to find the efficiency of individual machines. Okay, so now efficiency of motor we can compute from output by input. In motor we know the input, right? We can identify input here with some parameters, so we will just go with losses of the motor divided by input of the motor. Now 1 minus losses of motor is nothing but VTIA minus IAM square. Okay, no. Yeah. I think it is the loss for one single machine, and the total loss in the motor will be addition of IAM square RAM for motor and addition of IAG square RAG for the generator. You are getting where I am leading with this? This is, just you pay attention here. If we add this component, so I will get the total losses in the motor. Okay. So that's what I will do. VT into IA minus IAM square RM minus IAG square RAG by 2.
Sir,
Yeah.
to calculate the losses of motor, why we consider the resistance of generator?
Yeah. So see here we approximated, right? We calculated losses of combined motor and generator. This supply is going in combined set of motor and generator. Are you
Yes,
getting
sir.
this point? Yeah. So that's why that will come into picture. So both are coupled to each other. So let me plus IAM square RA divided by input is nothing but VT into or VT into IL, whatever, plus VT into IL. Okay, so this is the expression of efficiency of motor set. Now, what will be the efficiency of generator set? Again, same, just we add here, let me copy it. Okay, so what I will do, I will just remove this RAM and I will write RAG. Okay, so, but will it fulfill? I doubt. So, because VTIA will not be input to the generator, okay, so it will be something else. It will be this component I am telling you, the loss of generator, plus output of the generator. Okay. So output of the generator is what? VT into IA, right? Yeah. Any doubt in this expression? We will solve one problem, and I hope that will clear all the whatever you might be confused. Okay, this is a bit theoretical part. So let us go ahead with one problem. So I am providing you the data of it. Okay, supply voltage is 250 volt. Field current of the motor is okay. So I should not have revealed it, but since I have revealed, anyway, no problem. In further problems, you could identify. So field current of generator will be 2.5 amps. Armature current of generator is 60 amps, and current taken by the two armatures from the supply basically IA is 15 amps. Okay, RA for both motor as well as generator, since both are identical machines, so 0.2 ohm. We have to find out the efficiency of the motor and generator under this load. Okay, so first thing is, how much will be IAM? As I told, IAM will be IAG plus IA. So IAG is 60 plus IA is 15, so it will be 75 amps. Okay, to find out the efficiency of motor, we can write 1 minus loss in motor divided by input of motor. So input of motor, we can directly calculate VT into IAM plus VT into IFL. Okay, IAM we have calculated 75 here, and VT is nothing but given in the question, that is 250. Right, so 250 into 75 plus 250 into IFM is given in the problem, that is 2 amps. So it will be nothing but 250 into 77. How much it will be? 19250 watts. That is the input power of the machine. Now we just need to find out the losses in motor. That will be how much? Half VTIA minus IAM square RAM minus, sorry, this is minus IAG square RAG plus IAM square RM. Okay, so this is the losses of the motor. Now calculate it. VT into this IA is how much? VT into IA. How much will be IA here from the data? How much I can
15.
take the 15? Yes, exactly. So 15 will be the IA and VT is 250 minus IAM is 75, RAM is 0.2 minus IAG is 60, right? 60 square into RAG is again 0.2 plus IAM square RM. So 75 square into 0.2. So how much it will come out? Please calculate it. I will be back in 2 minutes. Okay.
Hello, bhai Neeraj. Hello, Neeraj.
Yeah. So how much is this value?
So 2077.5 watt.
2077.52 watt. Okay. So yeah, this is the value. Uh, Deepak, you are also getting the same?
Yes, sir.
Okay. Any other losses are required to be included? In this overall losses, we considered that input is only armature, but from total system perspective, you have
Sir,
to add
field
that
losses.
field losses. Yes. So VT into IFM will be equal to 250 into IFM is 2 amps. So it is 500 watts. So now I will just add it. So losses in motor will be 2577.52 watts. Okay. So now we can find out 1 minus 2577.52, 1 minus losses by input. Input is 19250. So efficiency of motor will be how much?
So 86.6.
86.6%. So that is the efficiency of motor, right? I hope you got the idea how to calculate efficiency of the motor. This is the most convenient way I have ever found to calculate from the Hopkinson's test all the losses and efficiency. Okay. Any doubt in this?
Sir, from this test, we can calculate efficiency and losses for both the machines
Yeah.
without any losses, without any big
Without
losses.
without any what?
Big losses, big practically losses like power consumptions.
Yeah, yeah, yeah. You can calculate. So basically, what is happening here? You are giving very less supply from the input side, and even though these machines are having high rating of the current, you are providing only 15 ampere of current from the supply current, right? From the supply, from DC supply, and still in generator 60 amps of armature current is flowing. In motor, armature is 75 amps of armature current. So this is kind of regenerative test where each machine will drive each other, and ideally they should continue to run for the infinite time, but practically they will have some limitations. Okay, so next part is the efficiency of generator. We got to know how to calculate the efficiency of the motor. Now, next part is efficiency of generator. Okay, so efficiency of generator, I told that it will be 1 minus losses in generator divided by losses in generator plus output of generator. Okay, so losses in generator will be, straightforward, just the same part plus different things. So, what is the value of this component? This particular component, can you compute?
So 952.5.
952.5. 952.5 plus IAG square RAG. Right? So it will be 60 square into 0.2. So that will be 3600, 720. So that will be 720 plus 952.5. It will be 720 plus 952.5. 1672.5, right? Plus, uh, just give me a minute. Yeah, so here, this is the losses. We have to add the field losses as well. So that field losses was nothing but how much? It was 500, right? So 1672.5 plus 500. So it will be uh, 2172.5 watt. Okay, so this is the losses in the generator. Now, input power we have already calculated for generator, right? No, output power of the generator, right? How much it will be output power of generator?
Sir, AB into IG, EG into IG.
Easy will be for input of the generator, right? Whatever coming out of the armature of the generator, output power of the generator we want here. So I can write VT into IAG, right?
Yes, sir.
So it will be 250 into 60. It is equal to 15,000 watt, right? So now we have all parameters. Efficiency of generator is equal to 1 minus losses is 2172.5 divided by 15,000. 2172.5. So it will be 2172.5 0.873. So it will be 87.3%. So efficiency of generator is 87.3% and efficiency of the motor is 86.6%. So pretty close values, right? And in some cases they are, almost equal if you ignore certain things. So that's why I think in some book you will also find efficiency of motor into efficiency of generator is equal to efficiency of current of current of armature generator, which uh, which is higher, armature of the generator or motor?
Motor.
Generator.
Armature, no, armature of generator is lower, but if you multiply two parameters, so the trick to remember is if you multiply two parameters, it will be lower value, right? So lower will be, I will write in numerator. So generator current I will write in the numerator and motor armature current I will write in denominator. So this is the very famous expression that you can see any textbook to see the derivation with certain assumptions.
Sir, what shows this expression?
Sorry, what is the source of this expression?
No, no. What is showing this expression? Like,
Product of two machines. If you know efficiency of one machines and current, so you could identify, right?
okay, it should be same. This expression should be same.
Yeah, and if both will be equal, then product will be almost equal. So yeah, this is just that to show that multiplication of them will not reduce very much if you do not have very much difference between these two parameters. So if you haven't given any armature current from the supply, so what will happen? IAG will be equal to IAM, right? Let's suppose
Yes, sir.
you are not giving any input current from DC supply, so IAG will be equal to IAM. Then in that case,
It should be
efficiency of
one.
one machine is inversely proportional to other.
And sir, both the machine have same ratings and same output power, so they should have same efficiency, right? I think.
Yeah, so from the numerical also you observe, right? Both are pretty close. No, that will not be exactly. Why? Because the current from the DC supply is going to the motor armature, not the generator armature. So operation
Okay.
of the two machines are different. It's not that both machines are different, but operation of the two different machines are different. So that difference you will be able to observe in the parameters.
Yes, sir.
Yeah, so that is all from my side, and I think this is the last week for us. So that's all from my side. Thank you very much for being patient and joining each of the sessions. That motivated me to prepare and present. Right.
Thank you so much, sir.
Thank you, sir.
Thank you. Thank you. Thank you very much.
Hello.